Hi. In today's lecture, I'd like to talk to you about the differential form of Gauss's law. Now, we're not going to go over the integral form of Gauss's law in this video, so if you haven't already seen or understand about the integral form of Gauss's law, you should go back and watch that video first. So first of all, a good knowledge of physics is also, for better or for worse, tied intimately to a good knowledge of math. So let's remember our vector calculus. For most of us, this would have been calculus 3, okay? And what I'm about to show here is a direct quote from my calculus textbook by Finney and Thomas, okay? So the outward flux of a vector field F, which has components m, n, and p in the i hat, j hat, and k hat directions, across an originated surface S with an outward unit normal in hat, equals the integral of del dot f, the gradient dotted with f, over the region D enclosed by the surface S. And so this could be written mathematically as the integral over the surface, or the double integral, of f dot n hat dA is equal to the triple integral, or the integral over the volume, of del dot f. Okay? Now, this is known as the divergence theorem of vector calculus. Okay? This is the divergence theorem. So today, what I'd like to do is apply this theorem from vector calculus to physics, and then we'll get more into exactly what this means. So let's look at our integral form of Gauss's law. All right? The integral form of Gauss's law says that the electric flux phi is equal to the integral over the closed surface of E dot n hat dA. Now here, E is the electric field. N hat is the surface normal to your Gaussian surface, and dA is integrating over the area. And that's equal to the enclosed charge divided by epsilon naught. If you're enclosing more than one charge, then you sum up over all your charges Qi, and then divide that sum by epsilon naught, the permittivity of free space. So that's if you have point charges. If you have a continuous distribution of charge, in order to find the enclosed charge, you might need to integrate over the volume rho dV divided by epsilon naught, where rho is the volume charge density, or the amount of charge per unit volume. It doesn't necessarily have to be uniform either. dV is your volume element, differential volume element. Epsilon naught's the permittivity of free space. Okay? So basically, the electric flux is how much electric field pierces through an area created by this imaginary construct, our imaginary Gaussian surface. And that amount of electric flux, Gauss's law says, is proportional to the enclosed charge with a constant of proportionality of 1 over epsilon naught. Now let's take that integral form of Gauss's law and look at our divergence theorem again and apply it. Okay? Remember, our divergence theorem said that the integral of the surface of f dot n hat over the area is equal to the triple integral of del dot f over the volume. So looking here, we can see that we have this E dot n hat dA, right? And that we can make an analogy to the F dot n hat dA. So that means that we could write the electric flux as E dot n hat dA, which would equal to the triple integral over the volume of del dot E dV. And then that would equal to 1 over epsilon naught times the triple integral over the volume of rho dV. Okay? So what this tells us is that we have this triple integral over the volume of del dot E, and then we have a triple integral over the same volume, right, of rho over epsilon naught. So we can take these arguments of our integrals, right, this del dot E and this rho over epsilon naught, and set them equal to one another, okay? So since, in other words, they're both integrated over the same volume, the triple integral of the same volume, then that means that since these are equal, the arguments of those things have to be the same. And we can write del dot E is equal to rho over epsilon naught. Okay? Now this is the differential form of Gauss's law. Del dot E is equal to rho over epsilon naught. And you can see that we derived this from our integral form of Gauss's law and using the divergence theorem from vector calculus. All right? Okay. So let's talk about this new formula that we have. Del dot E is equal to rho over epsilon naught. And let's break it down and analyze it from a lot of different viewpoints. That's what I'd like to do with the rest of this video. So first, let's talk about what this might look like for Cartesian coordinates. Remember that your gradient operator del is in Cartesian coordinates, the partial with respect to x times I hat, the unit vector, plus the partial with respect to y times j hat, plus the partial with respect to z times k hat. So that's our gradient operator. Now we can write our electric field vector as the x component of the field E sub x times I hat, plus the y component of the field EY times j hat, plus the z component of the field EZ times k hat. And then if we do del dot E, then what that means is that when you take a dot product, the x components multiply times one another, and then you add the y components multiply times one another, and then add the z components multiply times one another. So when you do this for del dot E, what you end up with is partial of E sub x with respect to x plus partial of E sub y with respect to y plus partial of E sub z with respect to z. That's your del dot E. And then you would then set that equal to rho over epsilon naught. Okay? So that's what it looks like mathematically. And now let's talk about what the units of that might be. So the dimensions of the electric field can either be written as newtons per coulomb or volts per meter. Here I've chosen newtons per coulomb. They're equivalent, of course. So I've got newtons per coulomb as the units of my electric field, and then the derivative with respect to x, partial with respect to x, that's got the del x on the bottom, the little differential change in x on the bottom. So that means that the units or dimensions of partial with respect to x is 1 over meters, right, in SI units. So that means that the gradient, partial EX with respect to x, would be newtons per coulomb per meter, or newtons divided by coulombs times meters collectively. So that's the dimensions. Now let's look at the right-hand side units. Del dot E is rho over epsilon naught. The dimensions of rho, it's a volume charge density, so the dimensions of rho must be coulombs per cubic meter in SI units. And the dimension of epsilon naught are coulombs squared per newton meters squared in SI units. And so you can see that if you take rho and divide it by epsilon naught, you're going to get newtons per coulomb times meters. All right? Now, why am I emphasizing this? I can't even tell you the number of homework assignments that I've graded where someone's had to do the gradient in a different unit or different set of coordinates and really messed it up, okay? So note here that going back to our 1000 level physics class, anytime you put something on the left-hand side and the right-hand side of the equal sign, if the units aren't right, it's not right, okay? The units must match. Also, when you add or subtract things, the units must be the same for every term. So that means that the units for partial EX with respect to x, partial EY with respect to y, and partial EZ with respect to z all must be newtons per coulomb times meters. So, why am I harping on this? Let's now look at what the gradient of the electric field looks like in different types of coordinate systems. The one I'm going to pick on first is spherical coordinates, okay? If you remember your Calc 3, okay, you might remember that when you're switching and doing the gradient in other coordinate systems, it's not as simple and happy looking as it is when you do it in Cartesian. For example, if I wanted to do del dot E in spherical coordinates, which is super common, right? Then what that would look like is you have an electric field vector, and that electric field vector has E sub r times r hat, plus E sub theta times theta hat, plus E sub phi times phi hat. In other words, the electric field will have components in the r hat, theta hat, and phi hat directions, okay? Now, all of those, E r, E theta, and E phi, still have units of newtons per coulomb because on the left-hand side you have your electric field, which has units newtons per coulomb. On the right-hand side, you've got your electric field times the unit vector for each one of those terms that you're summing. Remember that unit vectors are dimensionless. To get a unit vector, you take the vector and divide it by the magnitude, which means that you're dividing, for example, meters by meters, cancels out, dimensionless. So r hat, theta hat, and phi hat are dimensionless, which means that ER, E theta, and E phi all must have units of newtons per coulomb. Now, let's look at this gradient operator here for spherical coordinates. Del dot E, when you switch it over to spherical coordinates, is 1 over r squared, partial with respect to r, of, collectively, r squared times E sub r. That's from the first term, right, from the ER component. Next, plus 1 over r sine theta, partial with respect to theta, E theta times sine of theta, that's from the theta term, plus 1 over r sine theta, partial of E phi with respect to phi. Okay? And that's equal to rho over epsilon naught, which, as previously discussed, has units of newtons per coulomb times meter, or newtons per coulomb per meter. Now, ER, E theta, and E phi are all newtons per coulomb, right? So what's happening is you have these extra terms in here compared to your gradient operating Cartesian. You have this 1 over r squared out front, you have the r squared multiplying the ER, you don't have that in Cartesian coordinates, right? So if you look at it, what we've got here is inside the parentheses, r squared times ER, you have newtons per coulomb times meters squared. And then outside of the parentheses, you've got 1 over meters squared from the 1 over r squared. And then partial with respect to r, that's also 1 over meters, right? So you have 1 over meters cubed outside, right? And then inside you have meters squared times newtons per coulomb. And when you multiply all that through, the units are newtons per coulomb per meter for that first term. And I could make a similar argument for the second term and for the third term, okay? All right, so just remember that because, and here's where the mistake comes in, I can't even tell you on how many homeworks I've seen a student do this. They were working with something in spherical coordinates and they didn't know to look at their book and see how to take that gradient in spherical coordinates, and they mindlessly wrote out the following incorrect equation. Del dot E is partial of ER with respect to R plus partial of E theta with respect to theta plus partial of E phi with respect to phi. And that's just flat out wrong, okay? Not only because of all the calculus reasons why it's wrong and switching over from Cartesian to spherical coordinates and I think it's called the Jacobian, right? Not only because of that, which you're taught in Calc 3, but also from a Physics 1 perspective, the units ain't right, okay? Look, partial of ER with respect to R, that has units of newtons per coulomb per meter, but partial of E theta with respect to theta does not. It has units of newtons per coulomb because theta is in radians, which is dimensionless. And same for phi. Partial of E phi with respect to phi has units of newtons per coulomb, not newtons per coulomb per meter. And remember that you can't add dissimilar units, and you can't put dissimilar units on the same side of an equal sign. Okay? So don't do this. It's wrong. It's just wrong. Okay? Make sure that you remember that when you're switching coordinate systems to spherical or cylindrical coordinates, that you have to look up what the gradient operator looks like in that coordinate system and use that, okay? All right, don't forget. Number one mistake I see made on tests and homeworks with this stuff is that. All right, now that I've hopefully beaten that dead horse, let's talk about a system that we already understand and apply both the integral and the differential forms of Gauss's law and see if we can interpret what this might mean for us conceptually, okay? So the one that I've decided to pick on is one that I covered in a previous online lecture, and it's a uniformly charged sphere. And we're going to look at this uniformly charged sphere and see what the electric field is like everywhere using regular integral Gauss's law, and then we're going to apply the differential form of Gauss's law and see what happens, okay? So this might look familiar from a previous lecture. If you have a spherically symmetric charge distribution, and as shown here in orange, this is our sphere of charge. The total charge on our sphere is big Q, and the sphere has a radius little a, okay? Now we're going to look at what the electric field looks like for points outside the sphere. So in other words, we're going to look at a distance r, which is greater than a, from the center of the sphere and find the electric field. If you use the integral form of Gauss's law to do that, you would have the integral over the closed surface of E dot dA. Now remember, one of the tenets of Gauss's law is that you have to choose your Gaussian surface carefully. We covered this in the lecture, so go back and look at that if you've forgotten. But your electric field lines from a spherically symmetric distribution point radially outward in all directions, okay? And remember that for a Gaussian surface, you should pick a surface such that the normal to that surface is either parallel or perpendicular to the field lines at all points. Now here we've chosen one where the field lines point radially outward. We've chosen a surface normal that also points radially outward, so they're parallel at all points. Now we can also argue, because of the symmetry of the situation, that the magnitude of the electric field as you walk around that blue dashed line, which indicates our Gaussian surface, should be the same at all points, because we're at the same distance from the center of this uniformly charged sphere. So that means that we can pull our E out of our integral and then integrate over dA. Well, when you integrate over a sphere's area in spherical coordinates, you unsurprisingly get, as a result of that, the surface area of a sphere. And the formula for the surface area of a sphere is 4 pi r squared. So I end up with, for my flux, 4 pi r squared times E. Now, here, using Gauss's law, the integral over the surface of the electric field over the surface is equal to the charge enclosed by that surface divided by epsilon naught. For this particular problem, the Gaussian surface is enclosing all of the charge, big Q. So I can write 4 pi r squared epsilon naught is equal to big Q over epsilon naught because all of the charge is enclosed. And then I end up with my electric field magnitude of E is equal to Q over 4 pi epsilon naught r squared, which is equal to the Coulomb constant K times Q over r squared. Remember, K is equal to 1 over 4 pi epsilon naught. So, since I've already started this reasoning by saying that the electric field points radially outward, in vector form I could write that the electric field vector E is equal to KQ over r squared times r hat. Now, I'm going to take that formula that I found through my integral form and apply the differential form to it, right? E is equal to KQ over r squared r hat. If I plug that in, then that means that I have ER equals KQ over r squared. And then E theta and E phi are equal to 0. It has no theta and phi component, right? So I'm only going to be dealing with the non-zero part, which is this first term in my gradient function there, my gradient equation. So that means that I've got del dot E is going to equal to 1 over r squared, partial with respect to r, of r squared times KQ over r squared. Now, inside the parenthesis, I have r squared times KQ over r squared. The r squareds cancel out, which means that inside the parenthesis, I'm just left with K times Q. Now, both of those things are constants. And when I take the derivative of a constant, I get 0. So that means that this del dot E is equal to 0, because the partial with respect to r of K times Q is 0. Okay, fine. We can do the math, right? But what does that mean? And how am I to interpret that, okay? Here's what happens. The differential form of Gauss's law will tell you, given the field, what kind of charge distribution you have at that point of interest. So what this is telling us is that at that point r, which is radially away from the origin by the distance r, right, there's no charge. There's no charge there, right? That's all that's telling us. It can tell you what the charge distribution is at a point based on the field equation. That's what the differential form of Gauss's law does for you. This makes sense because we're outside of the charge distribution because r is greater than a, so there isn't any charge there. Okay? Now let's look at r less than a. So now we're inside the sphere. We're going to select yet again, a sphere is our Gaussian surface. It's indicated by this blue dashed line here. Okay? Now, at this blue dashed line, I am not enclosing all of my charge anymore because I'm not enclosing all of my sphere. I'm only going to be enclosing a fraction of that charge. So in other words, my enclosed charge, Q sub n, or Q sub in, is less than big Q, which is my total charge. Now, in order to figure out what my enclosed charge is, I'm going to have to integrate over rho dV, okay? So the left-hand side of my Gauss's law looks the same thing. The integral over the closed surface of E dot dA, just like before, is going to give us 4 pi r squared times the electric field E. And that's going to equal to the enclosed charge over epsilon naught. To find the enclosed charge over epsilon naught, I do the integral of rho dV. Rho here is going to be the uniform charge distribution. To do that, I would take big Q and divide it by the volume of my sphere radius A, which would be 4/3 pi A cubed, right? So I can pull that out front. And then I have 1 over epsilon naught there, so that's my rho. And then I integrate over dV. The integral over dV would be a triple integral over dV for a spherical distribution, for spherical coordinates, which is r squared sine of theta dr d theta d phi. So I've broken that out here into each one of the parts, the integral from 0 to r of r squared dr, and then the integral from 0 to pi sine theta d theta, and the integral from 0 to 2 pi of d phi. Okay? Now, the angular components, there's no angular dependence here, right? So it's going to give us the same thing as last time, which is 4 pi. Okay, so this integrals over the angles give us 4 pi. And then when we integrate r squared dr, we get r cubed over 3, which we then evaluate from 0 to r, right? And it gives us r cubed over 3. So Q enclosed over epsilon naught gives us this equation. Q times 4/3 pi r cubed over 4/3 pi a cubed epsilon naught. Okay? All right. So now setting my left-hand side and my right-hand side equal to each other for the differential form of Gauss's law, I end up with the equation that we found in a previous lecture for my electric field, which is that the electric field is QR over 4 pi epsilon naught A cubed, which is, if you solve for rho in terms of rho, you get E is equal to rho R over 3 epsilon naught. And that comes from the fact that rho is, of course, Q divided by 4/3 pi A cubed. Okay? So I've got rho R over 3 epsilon naught, and yet again the electric field is radial, right? It points radially outward from a positive charge distribution, so that's R hat. So this is my electric field equation, and now that I have my electric field equation, I can apply the differential form to it. So there's my electric field again. Here's what it would look like in spherical coordinates to do the gradient of the electric field, del dot E, right? Yet again, I only have an E sub r component, E theta and E phi are 0. So those terms, the second and the third term in this gradient equation, go to 0. And so I'm left with del dot E is 1 over r squared partial with respect to r of r squared times E sub r, and E sub r is rho r over 3 epsilon naught. Now the rho over 3 epsilon naught is a constant, so I can pull it out of the integral. And so I still have out front here this 1 over r squared from before, and then I multiply that times rho over 3 epsilon naught, and then I'm taking the partial with respect to r of r cubed, which is what I have left inside my parenthesis. The derivative of r cubed is 3r squared, and so then I have 1 over r squared, rho over 3 epsilon naught times 3r squared. The r squared cancels out, top and bottom. The 3 cancels out, top and bottom, and I'm just left with rho over epsilon naught. You're like, I just got the equation back again. How does that help? Okay, well, here's what it tells you. It tells you that when you are r away from the origin, and r is less than a, that you are immersed in the constant charge density rho. So it's telling us, given the electric field, what the charge distribution is like at that point. And it's a constant charge distribution with value rho. So, where are we going with this? You've got your Gauss's laws, your integral and your differential form. They're great. Both of them are awesome, but they're useful at different times. The integral form of Gauss's law is useful when you have the charge distribution, when that's known, and you want to find the electric field given that charge distribution. The differential form of Gauss's law is useful when you have the electric field and you would like to know the charge distribution at a point from that field. So, flip sides of the same coin. Now, what is this Gauss's law in both integral and differential forms telling us conceptually? What would you use in words to describe what Gauss's law means? Okay. So Gauss's law says that in order to have a net field flux, in order to have electric field lines coming out over an area, some net flux now, okay, and not a zero total flux if you add over the area, but a net flux, you have to have a source of charge inside that surface, okay? You have to have a source or sink of charge. In other words, it has to be positive or negative charge inside the enclosed surface. Now, if you have that source or sink of charge, then you'll have a field that diverges, okay? Remember what divergence means. The word divergence, the word diverge means to split apart, right? To split apart and go in different directions. So, for example, in the pictures over here, you have a field that's in green diverging from a point. In other words, they're all going off in their own direction away from that point. There is a divergence, right? Here is in English speak, convergence, or a negative divergence, right? It's coming in towards the point. So in other words, this is what happens for a positive charge, and this is what happens for a negative charge, right? The fields are, changing their directions at a single point. Here on the right in blue is a field which does not diverge. It's a constant field. It stays going in the same direction, and there's no divergence from that point, right? Always makes me think of that Robert Frost poem about the paths in the woods, okay? There's no divergence there. Okay, so I hope that makes sense, and I hope it's starting to gel for you. Now, there's one other point that I'd like to make in this lecture, and that's what kind of a charge distribution would cause a discontinuous E field, like a step function kind of in your E field. So let me show you here what I mean by that. I've got a step function in my E field here in blue, okay? And this is the kind of thing, for example, that we solved for in a previous Gauss's law lecture when we had this infinite plane of charge. Then what we would have is an electric field pointing to the right and then to the left on either side of that infinite plane of charge. So this is our electric field. Now, if you were to plot what the magnitude or plot the field along the x-axis, then pointing left would be negative and pointing right would be positive. And so that's why I have this step function right here where I have, for example, -3 values to the left of the origin and +3 values to the right of the origin. I just picked a random number, okay, so don't worry about that. So now let's talk about, using the differential form of Gauss's law, what del dot E would be at these various points. Okay, on the left here, plotting my electric field, remember that a gradient is just a derivative, and a derivative is just a slope, okay? So here on the left, for x less than 0, I've got a horizontal flat line for my electric field away from this infinite plane of charge. The derivative of that line is 0. Remember, rise over run. There is no rise, so the slope is 0. The slope is also 0 to the right for x greater than 0. Okay? In that case, I also have a flat line, and so the slope of that line is 0, and so that means that the divergence is 0 over there. Okay? So 0 and 0. Now let's look and zoom in at what happens at x equal to 0. Now I know in this plot you do see a little slope here, but that's just me and my bad plotting and not what would be happening in reality for an infinitely thin charged sheet, okay? So just pretend it's straight up and down, okay? So at this point, what would the slope be, okay? Remember that slope is rise over run, and so here we would have a change in rise of 6, but our run is 0, okay? And 6 divided by 0 is infinity. So that means that the gradient right here at x equal to 0, del dot E, is infinity, okay? So we have our step function electric field. So a step in the field comes about because of that infinitely thin charge distribution, at least in one dimension, okay? So remember our infinite sheet of charge. Let's say that, for example, the x equal to 0, so the yz plane, it's infinite in y and z, but in x it's infinitely thin. So that's what I mean by the one dimension here. It's infinitely thin in x. So this is our electric field. And that means that del dot E, which is the slope, that means that at that one point, your value of your charge distribution there, it's basically infinity, right? It's infinitely thin. And remember that a volume charge density is a charge per unit volume, right? And so if any one of the dimensions is 0, then that makes the volume 0, right, in 3D. And so that means that for a charge density, which is charge divided by volume, you'd be dividing by 0, which means you have an infinitely large charge density at that point. And I plotted that here. It just goes to a spike value. I'm trying to plot you a spike. But that's kind of what the charge density would look like in terms of a function. It would be infinitely thin, and it would be infinitely tall, okay? Now that is known as the delta function. There's actually a mathematical function which describes this kind of distribution, and it's a delta function or a Dirac delta function. Okay, it's known by both names. Symbolized by the Greek letter delta. Here I've plotted it as a function of r, but whatever, okay? The delta function has a value of 0 everywhere except at 0. And if you wanted to offset it, you could do the delta function of, say, r minus a or whatever, you know, put it wherever you want in space, okay? But it has a value of 0 everywhere except at where it's centered, okay? And if you integrate the delta function over the entire real line, the integral that you get is 1. So that's the definition of the delta function, okay? Now, in order for the integral of a function to go to 1 when its value is 0 at everywhere except a point, then that means that at the point it must be basically infinity, right? So what we could do is we could write the charge distribution of our planar sheet, and we might say that it's sigma times delta of r, right? The value of the charge density, the surface charge density, and then times delta of r at that point, okay? And if you go back to looking at these plots where I plotted the electric field versus our charge density in these two side-by-side plots, you can see that the derivative of the electric field step function, so the derivative of a step function is a delta function. Okay, so that's how you do it. So the integral of a delta function is 1, and the delta function is what you get when you take the derivative of a step function. Now, you would get this discontinuity in E anytime you have a big step or a jump of a huge value at a single point of your electric field, okay? So that might happen at the infinite plane of charge, like we talked about, but it also might happen if you're walking from left to right over a point charge, like is shown here, okay? So here you can see my electric field is pointing left if I'm at the left of the point, and it's pointing right if I'm to the right of the point. Now that's a point charge, but I could also think of it as looking down the pipe at a line charge, right? So anytime I have something that's infinitely thin in at least one dimension, I'm going to have that step function in my electric field. I'm going to have a big jump in value in my electric field, and that means that I've got that same discontinuity there, okay? Now, what we can say is that if you wanted to take and find the change of the electric field as you walk from left to right across this discontinuity, then you would say, for example, from an infinite plane of charge, you've got sigma over 2 epsilon naught pointing to the right, and then sigma over 2 epsilon naught pointing to the left. So if I wanted to find the delta E between those 2 points, it would be sigma over 2 epsilon naught minus a minus sigma over 2 epsilon naught, which gives me sigma over epsilon naught. So that's my magnitude of my change in the electric field when I have that kind of jump or discontinuity. And so what this tells us is that we have a surface charge density, basically. We have a surface charge over some three-dimensional volume if I have that kind of abrupt change in my electric field as I, plot it out. Okay, hopefully that all made sense. If you have any questions, let me know in class. And as always, I'll see you then. Bye.